네, 먼저 세미나에 초청하여 주신 부장님 교수님께 감사드리고요. In this talk, I will introduce modular curves and elliptic curves and how modular curves is applied to arithmetical elliptic curves. Now let me define the elliptic curves briefly. Elliptic curve is a projective smooth algebraic curve. Of genus 1. Then Riemann-Roch theorem implies that the elliptic curve is given by Weierstrass form, which has the following form. So let E be defined over field K, and if characteristic K is not equal to 2 or 3, then this Weierstrass equation is isomorphic to the following equation, which is simplified to this equation. The important property of elliptic curves is that it defines an abelian group. The group structure is given by the chord tangent method. So if you choose 2 points in elliptic curves, then if we draw a line through P and Q, then because it is a cubic equation, we have a third point. So if you let the third point P star Q, then the star does not define group structure because the star, under the star, there is no identity element. So if we take another point, which is reflection of this point along the y-axis, and this defines a group structure, and this defines an abelian group structure. So E has an abelian group. And over C, over the complex number C, then the structure is isomorphic to torus, where L is a certain lattice. So it has a torus structure. And over R, the structure is isomorphic to 2 copies of S1, 2 copies of the unit circle. And the important arithmetic property is that over the number field K, it defines a finitely generated abelian group. So if we denote the EK equal to the set of points which satisfies elliptic curve equation, and with the coordinates in number field K, and so here the identity element is given by 0, 1, 0 in P2. So in the projective plane, this line has 2 points, and another third point. The third point is the point at infinity. So this plays a role of identity element. So we have point at infinity. So this group is called the model Weil group. And Model's theorem is that the model Weil group is a finitely generated abelian group. So it has a free part and torsion part. So if the rank RE and the torsion part, if we denote the torsion part by E torsion K. So here E torsion K is a finite group, finite abelian group. By Nagel-Lutz theorem, then there is an algorithm which is easily computed. Then using Nagel-Lutz theorem, we can easily compute E torsion K for specific elliptic curve. But the rank part is unknown. It is very difficult to compute. So about the torsion part, Major's big theorem is that if we take the number field as the rational number field, then the torsion part is equal to one of the following groups. There are 15 candidates, and the cyclic candidates is G mod NG, where n equal to 1 to 10 and 12, and non-cyclic torsion has the following form, where n prime is equal to n prime 1 to 4. And over the number field, if k equal quadratic number field, then Kamienian and Major also classified exact torsion structure, and over the cubic field or quartic field, then Daeul-Jeon and B and Uisung Park and Schweitzer gave a partial result, which is not a complete structure, but we gave a partial result about the torsion over the cubic number field and quartic number field. Now in this talk, we will focus on the rank, and I will introduce some conjectures and some results. So let me give an example. Now, let E denote the elliptic curve defined by the cubic equation, x cubed minus 4x squared plus 16. In fact, this elliptic curve is equal to modular curve x1, 11, and has a very nice structure. First, let me focus on torsion structure. So we can easily calculate that 0,4 is in the model Weil group, and 0, -4 also is in the model Weil group. If we let y equal to 4, then 4 square equal x cubed minus 4x square plus 16. So if we factor this cubic factor, then we have another element. So when x equal to 4, then we have another 2 points. And by some calculation, we can see that all torsion points are equal to this 4 points, including point at infinity. So the torsion part has a order 5. And this torsion structure is equal to cyclic group structure. So if we draw a picture, then we can see clearly. So if we draw this elliptic curve in the xy plane, then we have this point, which we denote by P1. Another point is here. And we have another torsion point is here. So the graph is equal to in this way. So if we add this point and this point, then we get P1. So this is a tangent line. So this point, another point, this is equal to P1 plus P1. So this point is 2P. And if we draw a line through 2P and P, then this point is meets the double point. So 2P plus P is equal to 2P plus P. So this point is 3P. Then this point is 4P. And 4P plus P is point at infinity. So this structure is G mod 5G generated by this point. So later we will see that the whole structure of model Weil group is also equal to G mod 5G. So to introduce another conjectures related to elliptic curves, we have to work on finite field. Now let me denote the finite field G mod PG by FP. Then in our elliptic curve E, which was defined by E was y square x cubed minus 4x square plus 16. Now let me count the points on this elliptic curve modulo P. So let me denote MP equal to the number of points which has coordinates in G mod PG times G mod PG, which satisfies the congruence equation y square equal x cubed minus 4x square plus 16 modulo P. then we can calculate the number of points by ranging x and y from 0 to p minus 1. Then we have the following table. So let me calculate the NP up to p equal to 29. And we can easily calculate the number NP as follows. And if we denote another number, AP, which is obtained by P minus NP, then we can compute P minus NP from this table. Now, we observe that NP is equal to congruent to 4 mod 5, except for P equal to 2 and 11. P equal to 2 and 11 is called bad primes in the following sense. At P equal to 2, if we reduce the equation modulo 2, then we have y squared equal x cubed mod 2. So the equation has triple root at x equals 0 and y equals 0. So this does not define smooth algebraic curve. So it is not an elliptic curve. And at P equal 11, we see that x equal minus 1 is a one root. So if we decompose the cubic equation, then we see that minus 1 is double root, and another root is given by minus 5. So in this case, minus 1 is double root, so the cubic equation does not have three distinct roots. It does not define smooth algebraic curve. And in particular, if we change x equal to x minus 1, then the curve is y squared is x cubed, x squared, x plus 4. And and this defines tangent line and 0, 0. So in this case, the curve has a shape as in the singular point, there are two distinct lines. In this case, P equal 11 is called bad prime, P equal 2 and also bad prime. In this case, we distinguish these bad primes by terminology. We say that elliptic curve has additive reduction at P equal 2, and at P equal 11, we say that elliptic curve has split multiplicative reduction. And another language is that using discriminant delta function. Discriminant delta function is a discriminant function of this cubic equation. And in this particular cubic equation, delta is given by minus 2 times 8 and times 11. So the prime dividing discriminant delta function gives a bad prime. Now I will introduce L function, which is called Hasse-Weil L function. Which is defined by the product, infinite product, here there is two kinds of products. First product is finite product, and the second product is infinite product. And the first product is 1 minus AP p to the minus s inverse, and the second product is given by 1 minus plus p times. Then Hassel's bound is that the absolute value of AP is less than 2 root p. So the Hasse bound gives that the range of convergence of this L function. So this L function is defined in the right hyperplane, which is given by real part s is greater than 3 over 2. Now we can expand this L function as a series where we denote the coefficient an times n to the minus s. Now let me observe another quantity related to this elliptic curve. Now we consider infinite product for psi t, which is given by t times 1 minus t 1 minus t to the 11 to the square, and 1 minus t square 1 minus t to the 22 to the square, 1 minus t cubed 1 minus t to the 33 square. So in this way, we can define society. Then if we expand this product as a series, then we see that it has the following series expansion. We can expand this series as we want. So we observe that the coefficient at the prime power, first we observe that at the r prime, the AP was minus 1, 1, minus 2. We exclude bad prime. So in the good prime, we observe that the number circled before is equal to minus 1 and 1 and minus 2 and 4. So at the good prime, this number and that number are equal each other. So this is observation from Shimurama-Taniyama conjecture. So Shimurama-Taniyama conjecture implies that for every elliptic curve, we can define this function, which is the same coefficient at good prime. So let's define fz equal to psi exponential 2 pi iz. This defines a complex valued function. Then we see that this function is, we can show that this function is holomorphic and satisfies the following transformation rule. here ABCD satisfies AD minus 11BC is equal to 1. In another terminology, this matrix is called an element of the congruence group gamma 0, 11. So in general, there is a conjecture obtained from Shimurama and Taniyama. Shimura-Taniyama conjecture. If we let E is an elliptic curve defined over Q, then exists positive integer n and certain function fg. Here we denote we call this function, which satisfies this transformation rule, cost form of weight 2 with respect to the congruence group gamma 0, 11. Shimurama-Taniyama conjecture is that there is an integer n and holomorphic function fg, which is the cost form on gamma 0 n, such that the series expansion which has a series expansion. Here an is equal to the coefficients obtained from the L series. And this conjecture was proved by Brill and Conrad and Diamond and Taylor. These four mathematicians proved the Shimurama-Taniyama conjecture. And there is an L function from the cost form, which we denote LFS. So Shimurama-Taniyama conjecture is that LFS equal to the L function of elliptic curve. And from the theory of modular forms, the L function from cost form is defined over the complex whole plane. So this Shimurama-Taniyama theorem implies that the L function of elliptic curves extends to as a holomorphic function on the complex whole plane. So now let me introduce another conjecture from Birch and Sinot and Dyer. So because the L function can be extended to the whole plane, we can consider the value of L function at s equal to 1. So BSD conjecture relates the value to the rank of elliptic curve. Birch and Sinot Dyer conjecture, which is one of millennium problems. Now let's expand elliptic curve is defined over Q. If we expand the L function along s equal to 1, then we can expand in this way. Here R is equal to order of L function at s equal to 1. And BSD conjecture implies that R equal to the rank of elliptic curve, which is, we call the R from the L function analytic rank, and the rank is called the algebraic rank. So BSD conjecture implies that analytic rank of elliptic curve is equal to algebraic rank. So this conjecture was solved for the special case for R equal to 0 and 1. In this case, Gross and Jagier and Kolyvagin. The result implies that for R equals to 0 and 1, the BSD conjecture is true. And another rank, there are still open problem. So now let me introduce another conjecture which is related to rank. There is another conjecture called Goldfeld conjecture. Goldfeld conjecture is as follows. So to introduce Goldfeld conjecture, let me denote some notation. Like K equal to quadratic number field. Here we take D as a discriminant of quadratic field. And we denote another elliptic curve. Here, elliptic curve is defined over Q. And ED is another elliptic curve defined over Q, which is defined by the following equation. dy square equal x cubed plus ax plus b. And E also has an equation. This elliptic curve is called d-twist of elliptic curve E. And Goldfeld conjecture is about the rank of d-twist of elliptic curve. And Goldfeld conjecture is that the number of the discriminants d less than equal to x, such that order of s equal to 1 of L function of ED. So this order is analytic rank of the d-twist. So for R equal to 0 and 1. So this number has density of positive proportion. This implies that we can pick any elliptic curve ED from all d-twists. Then we can have half of them has rank 0 and half of them has rank 1. For the case R equal to 0, there are many known results. First result was obtained by Heath-Brown for R equal to 0. Heath-Brown from Oxford University. He considered the elliptic curve y square equal to x square cubed minus x and has some results concerning Goldfeld conjecture. And another result was obtained by Yu for more. elliptic curves, and James and Ono also obtained some results on the rank 0 case. But rank 1 case, there are not many known results. The first observation was obtained by Batjar. He proved some results of the Goldfeld conjecture concerning this elliptic curve X019, and the Bjorn from Seoul National University some result on the minus part on Jacobian, and Bjorn and John and me obtained infinite family of elliptic curves which satisfies the Goldfeld conjecture. So in the remaining time, I will introduce our results. So because our results has a complicated notation, so let me introduce our results, focusing on particular elliptic curve. So to introduce our results, we need some notation. So as before, let gamma 0 n denote the congruence group A, B, C, D in SL2G, satisfy C equal congruence 0 modulo n. And this group acts on a path plane. A path plane is defined by the following definition, which is a complex number as imaginary part greater than 0. Then gamma 0 n acts on the upper plane by Möbius transformation. So let gamma go A, B, C, D here, and Z is the element in the complex upper plane, and gamma acts on Z by Möbius transformation. So this action, we denote the quotient space gamma 0 n at H, which is called Y0n, and Y0n classifies n isogenes of elliptic curves. N isogeny means that certain homomorphism which has cyclic kernel so Y0n classifies, and Y0n applies to arithmetic of elliptic curves. And if we add some points to Y0n, which is called cusps, cusps is a point on the rational number. So let me focus on particular example. So there is a well-known theory from modular curve, and X011 is the union of Y011 and two concepts, 0 and infinity. Now let me define some infinite product with respect to Q. Q is a uniformizing parameter at infinity. It's given by exponential 2 pi iz. Let me define Dedekind eta function, which is given by infinite product 24th root of Q and product of minus Q to the n. Now, if we take the quotient eta z over eta 11z and take the 12th power of this function, then this function defines a function from x0, 11 to complex number. And this function is denoted by gg. And the pole of gg comes from infinity because this has an expansion q to the minus fifth plus blah blah. So the pole is given by at infinity. The divisor means that some quantity relating the 0 and pole of this function. So it has 0 of order 5 at cos of 0. And there is a abelian variety, which is called the Jacobian variety. It is defined by divisor class group, which is quotient of divisor of degree 0 and principal divisors. Principal divisors of the divisor coming from this kind of certain function, meromorphic function on this compact Riemann surface. And this abelian variety will be denoted by J0, 11. And we see that the function G defines a function, just function, but because it has order 5 element at 0 minus infinity, so it is order 5 in J0, 11. This element has order 5. So in another language, it is called the torsion point in Jacobian variety. So in general, the Weil reciprocity law implies that if we have a torsion point, this kind of torsion point, then this function multiplicatively extended to certain homomorphism to k star to the fifth. Here k equal quadratic number field q root d. In this case, we consider imaginary quadratic field. Here, the function is defined multiplicatively as a product of gp to the np. Then if we apply Weil reciprocity, we have a homomorphism. And because from Taniyama-Weil conjecture, Shimurawa-Taniyama conjecture, we have a map from x0, 11, which is a covering of elliptic curve. Here we also take the elliptic curve, y square equal x cubed minus 4x squared plus 16. which is modular curve x1, 11. There is a natural map from x1, 11 to x0, 11 because this modular curve is defined by gamma 1, 11, and gamma 1, 11 is just subgroup of gamma 0 n, which has the same condition on C and another condition on A and B. So there is a natural map from x1, 11 to x0, 11, and they are also elliptic curves. So this map is given by dual isogeny. So there is a covering. So we have also have covering to Jacobian variety of elliptic curve, which is also denoted Picard group to here J0, 11. So we have a map to Picard group of elliptic curve, which is isomorphic to elliptic curve. So we can define a map from elliptic curve to this quotient, which we denote by delta. Now we evaluate the function delta at certain particular points, which is called Higner points. So let me define the Higner points briefly. So as before, we recall that x0n classifies n isogenies. We will take certain particular isogeny from the elliptic curve R to n inverse. Here, I is an ideal in ring of integer of the elliptic curve. This ring of integer, and this is OK ideal. We simply denote ring of integer by O. Then it has a lattice structure, so this defines a torus structure. So we can view this torus as an elliptic curve. Here n is a prime, which splits complete to over 11. So if we impose certain condition, D is congruent to certain square mod 4n, mod 4, and here n equal 11, then this 11 splits in the complex quadratic number field. So if we pick n, then this defines an n isogeny. N isogeny, so it can be viewed as an element on x0, 11. So from the well-known theory of complex multiplication, then this point we will denote by as a triple O and R. R is an ideal class. And the well-known theory is that this point is defined on Hilbert class number field, Hilbert class field. This is called Hilbert class field. Now let the Higner point yk as a point defined by taking the trace of this point under the covering. We denote the covering x0, 11 to E by pi. Then this point is on the modular curve, and pi O n R is a point on elliptic curve. Now we take the point on elliptic curve as a yk, and this is called Higner point. Now let's denote tau equal to complex conjugate, and we denote y equal to ik minus yk tau. Then so because we have taken the trace, so this point, Higner point, is a point on elliptic curve defined over quadratic number field K. Then some computation using the theory of modular functions, in particular complex multiplication theory, implies that we can evaluate this function delta at Higner points, and we have a result as follows. If phi does not divide the class number is degree of Hilbert class field, over K, then we can compute that the value of delta function at Higner point is non-trivial. Delta y is non-trivial in K star over K star to the fifth. Then this implies that y has an infinite order. In particular, yk tau satisfies the following rule. Yk tau equal minus epsilon yk. Here epsilon is called the root number. Root number determines the parity of rank. In our elliptic curve, the root number is equal to 1. So in this case, this defines 2yk. And we easily see that this point is an d-twist of elliptic curve. Now we apply Gross and Zagius theorem, which shows that the value of L function at 1 products the value of L function of d-twist. In this case, we take the derivative, and this product is equal to multiple of some rational number, non-zero rational number, and the period of elliptic curve, omega e, and the period of elliptic curve, d-twist, and certain multiplied by certain height. This is called Néron-Tate height, 2yk. Néron-Tate height is non-zero, and so we see that the left-hand side is non-zero. This implies that elliptic curve E has rank 0. And elliptic curve ED, because Y has an infinite order, this implies that the rank of ED ED is greater than or equal to 1, and the derivative is non-zero. So this implies that ED has rank exactly 1. So in this way, we can prove the Goldfeld conjecture in this particular elliptic curve. So our method applies to a certain general case, which has no torsion point. So we considered certain family of elliptic curves, which is given by in this way. this curve has 3 torsion points at 0, 0, 3 equals 3. And the condition we need is that 3 does not divide class number. So there is a well-known theory. There is a positive density. The quadratic number field whose class number is not divisible by 3 has a positive density. So we can prove the Goldfeld conjecture for the family of elliptic curves with 3 torsion points. Now let me finish my talk.